Good morning. So, in the previous lecture, we have started discussion on governing equations for multiphase flow, and if you recall, we were discussing about the continuity equation. So, in terms of continuity equation, as I told you, for single phase flow, we have one temporal term which represents the changes within the control volume, and second term is an advection term which represents the transfer of mass across the boundaries of the control volume. For a typical single phase flow within a control volume, everywhere we have the same type of fluid present, and across boundary also same fluid levels. But when we consider a multi-phase flow, then we can have mixture of multiple phases present in a control volume. And when we are considering that, while writing our continuity equation for multi-phase flow in temporal term, when we write in temporal term, we write del by del t of rho n into alpha n, where alpha n is actually to account for the fraction of the volume present in the control volume of particular phase n. And when we write the advection equation, advection term, which represents the transfer of mass across the boundaries, then we write rho n into j n I divided by del xi. Okay, so over here, one small difference is from the single phase continuity equation. In single phase continuity equation, we were writing del by del xi of rho vi. But here we are writing del by del xi of rho n j n I, where j is referring to the superficial velocity. And the reason for choosing the superficial velocity is that in case of single phase flow, every time if some fluid is entering, at each and every point of this boundary, the same type of fluid will be present. Whereas in case of a multi-phase system, there can be some portion of boundary through which one type of fluid is entering, and there can be some portion of boundary through which some other type of fluid is entering. Okay. So over here, our interest is only to write the equation for a particular phase. That's why we are using its superficial velocity. Now after this, whenever we have a single phase flow and there is no source of fluid or sink of fluid kept within the control volume, there will not be any other mass transfer. Okay. But in case of multi-phase flow, what can happen? If we have a phase change system. Okay, so typically what happens in a phase change system, for example, if this is my control volume, and in this control volume, this is a vapor bubble, and this vapor bubble is continuously growing with time. Okay, so it's a boiling phenomena where vapor is growing in size. So once vapor is growing in size, then what will happen? The mass of vapor in this will increase and mass of liquid will decrease. Okay, so overall mass change within the control volume plus mass across the boundary has to be equal to the mass source or sink term for that particular phase n. Likewise, this is the example of a phase change system. Likewise, there can be reacting multi-phase flow. Okay, so in case of reacting multi-phase flow, if there are two reactants, then these two reactants can react with each other and these can form some other product. Okay, so in that case also there will be change in mass of the reactants or loss in mass of reactants and gain in mass of the products. Is this point clear? Now this is my, and this particular continuity equation is something which is called as individual phase continuity equation. Okay, now what is the meaning of this subscript n over here? The meaning of subscript n, we already know that n can be ABC or it can be 1, 2, 3 depending upon the which one we want to use to designate our phases. So let's consider that in a multi-component system, n is equal to A, B, C, D, etc. Okay. So in this scenario, what will happen? The continuity equation for phase A will be del rho A into alpha A by del T plus del Y del Xi of rho A into JAI. Is this point clear? And this has to be equal to IA, source term for phase A. Okay. Similarly, if I have to write for phase B, then what it will be? Rho B into alpha B divided by del T plus del by del xi of rho B into JBI equal to IB. Okay. Likewise, you can write for all the phases. Is this one clear? Now, if you add all these terms, what you will be getting? Del by del T of rho A alpha A plus rho B alpha B plus so on up to like this, and del by del xi of rho A JAI plus rho B JBI plus so on up to like this, and in the right hand side I will be getting IA plus IB plus IC plus so on up to like this. Okay. Now, what is this quantity? This quantity can be simply written in the terms of summation of rho n into alpha n over the n. Is this one clear? So this can be simply written in terms of summation of rho n into alpha n. And second quantity, this addition term in the bracket, it can be written in terms of summation of rho n into jni. Is this point clear? So this can be second quantity. Now, what is this first quantity, rho n into alpha n summation over the n? What is this quantity? Please recall from the previous lecture and tell me. What is summation over the n, rho n into alpha n? This is rho, mixture density. Okay. So it means first term I can write as del rho by del T. Is this point clear? Where? Because this term is equal to rho, mixture density, plus del by del xi of summation n rho n into jni. Okay. What will be there in the right hand side? IA plus IB plus IC. Now, let us understand with a two-phase system. With a two-phase system, if I am having two phases, liquid plus vapor, okay, and if I say phase change is happening, then for liquid, phase change is happening from liquid to vapor, say phenomena is boiling. In that case, IV term will be positive, okay, source term for vapor will be positive, because in boiling liquid mass gets converted into vapor. So vapor mass will be generated. So that's why IV will be positive and IL will be negative. If I consider that I have only two phases present, then if one quantity is positive, other will have to be negative of the same magnitude. Okay, very simple thing. Say this is my control volume. In the control volume I have liquid and vapor. If I say that this much mass of new vapor is generated, so this much mass of new vapor has generated. So it means this is my IV and this IV term is, sorry, yeah, so this much, I have used the wrong notation. Say this was the original situation, this was my liquid and this was my vapor. Now because of the boiling phenomenon, if this much mass of liquid has got converted into vapor, okay, so this much mass is converted into vapor, so this will be my what? IV amount, which has been converted because of the phase change into vapor. Now if you see, liquid mass has decreased by what amount? This was the initial liquid mass and this is now final liquid. So it means liquid mass has decreased by the same amount. Okay, so this has become minus of IL. So when I will be adding these two source terms, then ultimately to write down the combined continuity equation, then these two will be giving me magnitude equal to. Is this point clear? Now likewise, when I have n phases present in the system, so in terms of n phases, what will be happening? Mass of one may be increasing, say A phase mass is increasing. But ultimately, while A's mass is increasing, some other phase mass has to decrease, from somewhere it has to come. So it may happen that say B is converting into, part of B is converting into A, part of C is converting into A. So then B and C has become negative. Then say D is also positive. So likewise what will be happening? Some masses will be increasing for some phases, for some phases masses will be decreasing. Okay, because this additional source term is coming because of either the phase change process where one phase is getting converted into other, or it is coming because of the reaction between the different phases. Okay, so in reactions also what will be happening? Part of reactants which are reacting together, these will get converted into product. So it means overall it may happen that in individual phases some mass is entering, some mass is going out. Okay, but everything is happening inside a closed vessel. So if everything is happening inside a closed vessel, so if I combine all the components inside that, say, closed control volume, I am not saying closed vessel means the masses cannot move across boundary. Masses can move across boundaries because we are considering control volume. But ultimately, whatever the changes are there across the boundaries, that we are already accounting for in the second term on the left hand side. Okay. So over here, our major concern is about the source term. So whenever we are talking about source term, for source term, everything is happening within the control volume. Okay, so it means within the control volume, only if one phase has to convert it into two, so other has to also gets converted into the previous one in order to have the mass balance. So that's why in right hand side what will happen? If I add all the source terms, then these will be equal to 0. Okay, so this is equal to 0. So whatever this equation I have got, this is called as combined phase continuity equation. Is this one clear? So now you can see the difference. In individual phase continuity equation, we have some source term on the right hand side. But in the combined phase continuity equation, it has almost evolved like the single phase equation where right hand side is equal to 0. Is this one clear? So this is the point I have explained over here, that ultimately sum of all the source terms, if I do, that has to be equal to 0. And likewise, if I do summation of this continuity equation, then this will be my equation, and in the left hand this first term can be written in terms of rho n into alpha n will become rho, and in the right hand side what can be done, this j and I can be replaced with alpha n into u and I. Is this point clear? So this is my combined phase continuity equation, and one important point we have to understand that in the combined phase continuity equation, this second term, we know that j and I is equal to alpha n into u. So this I have replaced alpha n into u. Now let me make one assumption. From here I will make one assumption that u and I is equal to ui. What is the meaning? What is the meaning of u and I? U and I is velocity of nth phase in ith direction. Okay, I am writing this equal to ui. So it means that I am assuming that all the phases are moving at constant velocity, and that velocity in ith direction is equal to ui. Is this point clear? So here assumption is when I am writing u and I is equal to ui, the physical meaning is all phases moving at same velocity in ith direction. Point is clear? If all the phases are moving at same velocity, then it means there is no drift between the phases which we are considering. So it means that this u and I now I can simply replace with ui over here, and what will happen? This ui will be a fixed quantity now for all phases. So if ui is fixed, I can take it out of the summation. Ui can come out of the summation, and inside the summation what I will be having simply rho n into alpha. Is this one clear? Because summation I am doing over the n, okay, not in terms of I. So that's why ui can be taken outside. So if I do so, this again can be written in terms of rho. So I will be getting del rho by del t plus del by del xi, rho ui is equal to 0. This particular continuity equation is called as mixture continuity equation. So in this equation it is assumed that the particles are so small and so much dispersed within the phases that their velocities are almost identical to the velocities of the surrounding continuous phase. Okay, so in this way we can say that our multi-phase system or multi-component system is actually, well, though there cannot be 100% mixing because phases are immiscible, but still it is in the range of, in the origin of well dispersed or well mixed flow. Okay, so that is the reason whatever is present within the control volume, we are applying directly the mixture properties to estimate the average properties, and whenever we are writing the continuity equation, we are treating that complete mixture as a single phase which is constituting of the properties identical to that of mixture properties. Is this point clear? That is the reason I am calling it as mixture continuity equation. So you can clearly understand that this type of formulation will be only applicable for this type of flow, well mixed flow. Okay, if you try to apply this situation for say, if you try to apply this situation for well separated flow, there, because these velocities cannot be same, so this type of continuity equation will not serve the purpose. Okay, this will give wrong outcome. Now comes next part, which is area averaged equation. And this is typically employed for 1D flow assumption. Okay, so whenever we do study the flows, then many times we make one assumption which is called as the assumption of one-dimensional flow. Okay, so typically we know, can you tell me from basic fluid dynamics, what do you understand by 1D flow? Yes, we consider the flow only in one direction, but it is not always true that other two directions are infinite. 1D flow can be applied for a pipe. Rather than that, if you have a pipe, what is velocity profile in a pipe? Say flow is laminar, then parabola. Okay, so you will be having this type of velocity profile. Now here what is happening? if I fix the coordinate system, this is r, this is z, then you can see that this velocity is varying in both r and z direction. So you can be, unless or until it is a fully developed steady incompressible laminar flow, I am not going for that. In general, you will be function of r and z in a cylindrical pipe. Is this point clear? Now, at this point itself, I can also define at the same location some velocity which is average representative of this velocity profile. Is this point clear? All are clear about this point? So, whenever we do study this Hagen-Poiseuille flow, one we define u as function of r and z, and other term, if you recall, we define u z average. Okay, what is the meaning of u z average? At any location z, what is the average representative of velocity of fluid? All are clear with this point? Now, there can be some situations, or even if I have the complex situation, then analyzing complex situation in, say, two coordinate system where dependence is happening upon r and z, that will be more complex. So initially, if I have to start the solution for any unknown situation, I can also start with one assumption that the parameters which I am considering, these parameters are nothing but cross-sectional averaged quantities. Is this point clear? Cross-sectional averaged or area averaged quantities. Is this point clear? All are clear with this point? So it means any quantity which I will be using, I will try to define that this quantity is uniform at almost the entire area. Okay. So for this velocity profile, if I make the assumption of one dimensional flow, that velocity is only varying in z direction, that u is only a function of z, then what I need to consider, whatever the velocities I need to define all these cross sections, these velocities will be a single value, u z1, u z2, u z3, etc. And these u z1, z2, z3 will be the cross-sectional area averaged representative of this entire. Is this point clear? So this type of assumption when we make, that is called as the assumption of 1D flow, or I can say the area averaging of the equations. Okay. Now you see, whenever we are discussing about the area average quantities, the first term over here, what does it represent? It represents the changes in mass only within the control volume. Okay. So here involvement of area is not taking place. If this is the control volume, where involvement of area will come? Involvement of area will only come when the properties are moving across the boundaries, because their only cross section is coming within the control volume. It will be cross-sectional boundary will not play any role. So that's why first term of the continuity equation will remain as it is when I will be talking about area average equation. But when I will be discussing that how much mass is actually entering, when I will be discussing how much mass is entering, first important point is, in advection term, I will not be having now multiple principal directions. I will be only have single direction. So that is the reason you can observe that when I am writing simple continuity equation, then in the second term, del by del x term is involving I. Because for a three-dimensional system, I will be having x, y and z. Okay. So when I is 1, then I am referring to x. When I is 2, I am referring to y. I is 3, I am referring to z. Okay. But when I will be talking about area averaged quantity, then my xy will be becoming cross section and only x will be becoming the direction along which properties are moving. Okay, so that is the reason that when I am writing this del by del x term, only I am writing x. So it means now it will not be having dependence on other direction. This point is clear. Now next point is, because I have to define the area averaged quantity. Okay, so for defining area averaged quantity, what I have done, when I have written rho n alpha n into un, because alpha n and un can vary at different points of area. Is this one clear? So I have multiplied these quantities with area, and because this area is now making it dimensionally inconsistent, so outside I have divided with area in order to define averaging over the complete process. Is this one clear? So in area averaged equation, first point you have to remember is that dependence is only along a single direction. So that's why we are getting del by del x, and to account for averaging of properties over the area, we are multiplying area with this term, and outside we are doing 1 by a. Okay. For example, if you know that any property or anything which is varying with, say, area, then what we can do? We can do its variation multiplied by dA and then 1 by a of integral that, in order to define the average of that. So likewise what we are doing, we are putting this area in multiplication and 1 by a outside. Is this one clear? Now, and of course, because this equation is for a nth phase, so that's why in the right hand side I am having the source term. So I can call this equation as area averaged individual phase continuity equation. Area averaged individual phase continuity equation. Is this one clear? Now, what I do, if I add the terms for all the n phases, then what will be happening? For first term, I will be getting del rho by del t, and in the second term, because I am doing summation over the n, okay, I am not doing summation over area, I am doing summation over the n. So that's why area can be taken out of the summation symbol, and all other quantities will be coming inside summation, and summation of in will become equal to 0 in the right hand side. Okay, so this is nothing but area averaged combined phase continuity equation, AACP. Is this one clear? So this equation has become area averaged combined phase continuity equation. What is this equation? You should be able to tell me now. So what we have done now, we assumed that un is equal to u. It means velocity of all the phases is same. So if velocity of all the phases is same, then this u can come out of the summation, and inside this quantity will become summation over this will become rho, so rho au. So it means this is nothing but area averaged mixture continuity equation, AAMC, area averaged mixture continuity. Okay, is this one clear? So all these equations will be applicable when you are considering variations only along a single direction. So you are making the assumption of one dimensional flow or area averaged flow. Okay. Then we have next. Again I am having the continuity equation. But in this continuity equation, first term is as it is. In the second term, this I have replaced with J and I have replaced with alpha n into U and I. Rho n alpha n into U and I. Okay? Now let's assume, what is the name I have written? Disperse phase number continuity equation. Okay. Now, till now, whatever equations we have written in terms of the volume fraction of each phase. Okay. Now our interest will be to write continuity equation in terms of the number of particles of the dispersed phase present in the system. Okay. So this can be a control volume, and in this control volume I can have large number of particles present. Is this one clear? So I can have large number of particles present. So typically there are certain modeling techniques which are called as population balance methods. Okay. So in case of population balance methods, what is done? Instead of using volume fraction as criteria, if we are able to anticipate that countable or finite number of particles are present in the system, then instead of tracking their volume fraction, we can directly track their number. Is this one clear? So, what will happen if I assume that all my particles are actually solid? If all the particles are solid, then what will happen? Typically, solid particles are considered rigid, and solid particles will not be having any breakage. Okay. So if we assume that solid particles are rigid and these are not breaking, then if at any point of time Nd is the number of particles present over here, then change in Nd will be only because if some particles are entering or some particle leaving the boundary. Is this one clear? Second situation could be if these particles are not liquid, but these are not solid, but these are fluid particles. Fluid particles how? If I consider that this is a continuous phase, okay, so continuous phase is liquid and all these are nothing but air bubbles. Then at any point of time I can have some NB number of bubbles. If a larger bubble is breaking into two, then also there will be change in number of bubbles. There can be two or more bubbles which are joining together and forming a single larger bubble. Okay, so there also number density of these bubbles will be changing. Likewise, if I do the inverted situation could be where continuous phase is gas and dispersed phase is droplets of the liquid. So droplets of the liquids are also deformable, and number of drops of liquid can also merge together to form a large drop. Is this one clear? So this type of approach is actually called as population balance approach. So if we have to do modeling of the population balance approach, then our equation of continuity should be in the form of number density. Okay. And one important aspect is whenever we apply this approach for fluid particles, for bubbles and droplets, then depending upon their size, velocity, field and surrounding fluid medium, we use some models which tells us under what conditions breakage of a larger bubble will be happening or coalescence of multiple bubbles will happen to form a single bubble. But at the moment we are not going into these final details. Okay. So here let us assume that Nd is number of bubbles, let me make it generic, number of dispersed phase particles per unit control volume. Per unit volume. Is this point clear? So what I have done, whatever the control volume I am having, in its unit volume, ND is number of dispersed phase particles. Is this point clear? Now, what will be then the time rate of change of this number within the control volume? That will be del by del T of ND. Okay, because we write continuity equation on per unit volume basis. If I do not use this per unit volume term over here, then in this continuity equation we have to use ND by V. But as I have defined ND as the number based on per unit volume, that's why I am simply writing del by del T of ND. Is this point clear? Plus del by del Xi of ND will be number of dispersed phase particles, and UDI will be their velocities in ith direction. So if a particle, depending upon its velocity, if velocity of particle is positive, it will be moving out of the boundary. If velocity is negative, also depends upon at which phase we are calculating, because here positive velocity at this phase will indicate it is entry. So depending upon the orientation of the phase and the velocity of this particular velocity of particle, this particle can go in and can come out. So this second term over here represents the transfer of particles across boundaries of control volume. Okay, say this is a room. In this room, earlier say we were around 13 people. Now 3 people have moved across the boundary, so whatever change will be there in the number, that we are actually trying to find. Okay. So this is my dispersed phase number continuity equation. Now one important point. Earlier you have seen that whenever we are writing this dispersed phase equation, earlier what we were doing, or any particular phase equation, we were using the source term over here. Okay, we were using the source term. Now we are not using the source term. Ultimately, because any change in number, at the moment we are assuming the particles are rigid. Moreover, any change in number within the control volume, that has to be accounted for through some separate numbers. So at the moment I am not accounting for that particular variation. Okay, so I am simply assuming that dispersed mass is always remaining present in the form of particles, where number of these particles can increase or decrease. Okay. Now one simple point, can I define volume fraction if I know number? What will be volume fraction? Number of particles, say volume of each particle is Vd. Vd is the volume of each particle. Okay. Now what is this number? This number is number of particles per unit volume. So already if I have 100 particles, what will be my volume? And say volume of each particle is 1 mm, then it will be 100 1 mm cube. But if I say my unit, whatever the volume I am considering, that is also of 1 mm cube only, then this will be divided by 1, and ultimately it will be becoming fraction of dispersed particles. So likewise, because ND I have already defined as the number on per unit volume basis. Okay, so when I will be multiplying ND by VD, then per unit volume is automatically considering in the denominator. So this multiplication will be giving me volume fraction of the dispersed phase. Is this point clear? And one assumption we have made over here, that all the particles are of identical volume Vd. Is this one clear? So all the particles are identical, having volume. Now I can also write the previous equation. What was the previous equation? This. In this previous equation now, I can replace alpha n with what? Sorry, alpha d with nd into Vd. So del by del t of nd into Vd into, is this one clear? And in the second term also what I have done, I have replaced alpha with nd into Vd. All are clear with this idea? How I have got this equation? So this equation is nothing but del y del t of rho d into alpha d plus del by del xi of rho d alpha d into udi. Okay. Now alpha d I have replaced with nd into vd. Here also alpha d is nd into vd. And this was equal to I of dispersed phase. So that is all are clear with this point. Now what I can do, this rho d and vd I can consider as 1 or u, and this I can consider v. Likewise, these two can be u and this can be v. So if I do so, and if I apply the chain rule of derivatives, then ultimately I will be getting id equal to nd will become common, del by del t of rho d vd plus udi into del by del xi of rho d vd. There will be one more term plus udi into del nd by del t plus del by del xi of nd into udi, and this term from the first one will be equal to 0. All are clear with this point? So from first one this will be equal to 0. So ultimately I will be getting my id equal to nd times temporal term plus advective term. What is temporal plus advective term? Equal to, what is the definition of total derivative? Please tell me. Total derivative or substantial derivative, d by dt. Del by del t plus u dot del. So this is local term plus this is advection term. So here you can see this is del by del t of rho d into vd, and this is udi means this u, and then del by del xi. So this del operator is equal to del by del xi also. So del by del xi of rho d into vd. So what it will become? This will become d by dt of rho d into vd. One important point, with this capital D total derivative, it is this small this capital D is also used in subscript. Why? The reason is this velocity over here is coming for dispersed phase, and all these quantities inside are specifying dispersed phase, but outside in advection term this velocity is coming off the dispersed phase. So total derivative of is defined by considering velocity of dispersed phase in the advection term. That is the reason this dd is used in the total derivative. Is this one clear? So from here id is equal to nd into dd by ddt of rho d into. Okay. So from here what will be id by nd? Simply dd by ddt of rho d into vt. So it means id is mass source term of the dispersed phase. So mass source term of dispersed phase per unit number of dispersed phase particles is equal to total rate of change of the dispersed phase mass per unit control volume. Okay. This is how you can physically interpret this particular equation. Now there is another way of representing this dispersed phase continuity equation. What is eta is number of dispersed phase particles per unit liquid volume. What was ND? ND was number of dispersed phase particles per unit total volume, and eta is number of dispersed phase particles per unit liquid volume. So what I can say that for a control volume having VL as liquid volume and V as total volume, for that particular control volume I can represent that eta into VL will be equal to eta D into what? V. What will be eta D into V? If ND is number of particles per unit volume. Okay. So what is the volume, total volume? V. So ND into V will be becoming the total volume of the dispersed phase, and if eta is number of particles in the same control volume but per unit liquid volume, then the dispersed phase will become eta into VL. Is this one clear? What will I get from here? Eta equal to ND into V by VL. If I consider that alpha D is equal to VD by V, then what will be alpha L? 1 minus VD by V? Only that will be alpha L. So VL by V will become 1 minus alpha. All are clear with this point or not? Eta is number of dispersed phase particles per unit liquid volume. Okay. Of course, in order to make it more accurate, you have to also multiply volume of each dispersed phase particle, but that we are choosing identical, so this small VD will be cancelled out. Is this one clear? All are clear with this idea or not? Any doubt? Okay, let me explain you this again. What is eta D? Number per unit volume. Okay. So when eta D is divided with volume, what it has become? Only number. Volume has got cancelled. Okay. So this has become total number of dispersed phase particles in control volume. Is this one clear? Now in the same control volume, I have VL amount of liquid and eta is number divided by volume, but whose volume? Only volume of liquid. So eta into volume of liquid will be total number of dispersed phase particles in liquid volume. Is this one clear? So this is total number. Now if I say that this total number in the control volume is multiplied with volume of each particle, which is small vd, then eta D into V into small vd will be equal to what? Total volume of dispersed phase particles in the control volume. And in the same control volume, if VL is the liquid volume, then this has to be equal to eta into VL into Vd, because eta into Vl represents the number of dispersed phase particles in the liquid volume. Is this one clear or not? So from here, if you do, then you will be getting eta as eta d by 1 minus alpha. Likewise, I am not doing it again, but you can also try that if you multiply this eta minus alpha eta equal to eta d, and then here alpha if you replace in terms of volumes, then you can get eta d equal to eta by 1 plus eta. Similarly, if you do more algebraic manipulations, you will be finding alpha equal to eta into V by 1 plus eta V. Where what is this V? This is important to know. This is volume of each dispersed phase particle. Is this one clear? This is volume of each dispersed phase particle. Now what you can do, in your previous equation, you can replace, so this was the previous equation, here this rho d Vd you can actually replace in terms of eta and Nd, okay, and ultimately what you will get is that del u d by del xi equal to eta by 1 plus eta v. Do you have, any one of you have class? You can leave. So del u di by del xi equal to eta by 1 plus eta v into dd by ddt of vt. So what is this? Can you tell me what is del u by del xi? From basic fluid mechanics, what is del u by del x plus del v by del y plus del w by del z? What we call this quantity? Is this equal to volumetric strain? If you refer to your kinematics part in the fluid mechanics, this quantity is nothing but equal to volumetric strain. So over here, del u di by del xi, this I can say that volumetric strain for dispersed phase is equal to this some number density times d by dt of volume of each dispersed phase particles. Total time rate of change of volume of each dispersed phase particle. Is this point clear? So from here one important conclusion comes that total volumetric strain of dispersed phase is directly proportional to total time rate of change of volume of each dispersed phase particle present in the control volume, and this proportionality is balanced by this number density formulation. Is this point clear? So this is an important conclusion. It means that in your control volume, if 1000 particles are present, then what is the time rate of change of each and every individual volume of that particle, that will be able to directly correlate the volumetric strain of the entire dispersed phase. Okay, but only thing is, here assumption is that we are assuming the particles are of same volume. Now let's not discuss Fick's law at the moment, because it will be majorly important only for reacting species. So we'll stop at this point and we'll discuss further in the next class.